This is such a beautiful application of linear algebra ideas that if you have an n by n matrix A, and A is nilpotent, which means that some power of A is equal to the zero matrix, then we can conclude that actually the nth power of A is equal to the zero matrix. So as an example, for example, if you had a 2 by 2 matrix A, so if A is a 2 by 2 matrix, and if you know, for example, that A to the 10 is equal to 0, actually that implies that A squared is equal to 0. So it's not possible for A squared to be non-zero, but a higher power of A to be 0. And that's really beautiful. That's like a very nice characterization of what these matrices look like, because then, for example, you could sort of solve for A in this kind of equation with A squared is 0. You only have to take the square of a matrix rather than a 10th power. But it's also just a beautiful conceptual property. So how are we going to prove this statement? So let's just dive right into it, and we're going to love this proof. So what we're going to do is a proof by contradiction. Okay, so here's the proof by contradiction. So the contradiction is going to be assume that A power n is non-zero. Okay, so assume that A power n is non-zero, and if A power n is non-zero, that means there is some vector v, right? There's some, say, column vector, if you like, n by 1 column vector. A is kind of thinking of as a transformation from Rn to Rn. So you can take some vector v in Rn so that we know that A to the nv is non-zero, right? Because A to the n is non-zero, so some multiplied with some vector, it's non-zero. Okay, so we can say there's some v in v such that, so this is st, such that A to the nv is equal to something that's non-zero. Okay, so however, we know that A to the k is 0 for some k. So of course that k has to be greater than n, otherwise A to the n times v would be 0. But what we do know is that k is greater than n, and therefore we can conclude that there is a minimal such k, so that A to the kv is 0. Okay, so let k be minimal. So I'm going to say, let me call it a different letter. Let's say let m be minimal such that A to the mv is equal to 0. Okay, so A to the mv is equal to 0, and of course we know that m is going to be greater than n, right? So we know that much. Now we've got something, we've got some basis. So how are we going to proceed with this? This is going to be so beautiful. So we're going to prove a linear independence of some vectors. All right, so take the vectors. Okay, so let's take the vectors v, a squared v, all the way up to A to the nv. Okay, A to the n times v. These are all non-zero vectors. We know that, okay, because A to the nv is non-zero, so no lower power of A times v can be 0 either. So we've got n plus 1 of these vectors. Okay, so that's very important. We've got n plus 1 vectors here. N plus 1 because you start with v, then av, so A to the 0v, A to the 1v up to A to the nv. N plus 1 vectors inside Rn, okay, because A is an n by n matrix. So n plus 1 vectors in Rn, we're going to show they're linearly independent, which is then going to be a contradiction because you can't have more than the dimension number of linearly independent vectors. For example, you can't have 3 vectors in R2 that are linearly independent. And let's actually review what linear independence is as well. So basically we're going to show that if a linear combination C0v plus C1av plus dot 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 plus Cn a to the nv, if this is equal to the 0 vector, okay, so there's some combination of these vectors equal to 0, then that implies that Ci is 0 for all I. Okay, so all the coefficients are 0. So how are we going to prove this? We're going to do an inductive proof, and it's so fun. Okay, it's going to be so cool. So the first thing we're going to do is we're going to take this relation, okay, that C0v plus C1av up to Cn a to the nv is 0, and we now want to show all the coefficients are 0. Let's act, okay, let's take our linear transformation A, let's take a to the m minus 1, okay, and let's apply that to both sides of this equation. So if we apply that to both sides of this equation, we get a to the m minus 1 times C0v plus dot 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 plus Cn a to the nv is equal to a to the m minus 1 of 0, which is just 0. 0 vector is unmoved by a or any power of a. Now what we do is we get that this is going to be C0 times a to the m minus 1v plus, you can keep going, plus C1 a to the mv plus dot 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 plus Cn a to the m plus n times v, and that's going to equal to 0. What's so cool about this? Well, remember that m was minimal, so that a to the mv was 0. That means a to the m minus 1v was non-zero. That means that if you look at this equation, all the other powers of a on v are going to be 0, right? Because a to the mv is 0, so higher powers of a on v are going to equal to 0, but this is going to be non-zero. A to the m minus 1v is non-zero. But that must imply that C naught is 0. You're scaling by 0 to get the 0 vector because a to the m minus 1v is non-zero. So therefore we conclude that C naught is 0. So we've got C naught is 0. That's pretty good, cool. Okay, so now we're getting one step closer. Now we can keep going. So now that we know C naught is 0, our relation is actually C1AV plus C2A squared V plus dot 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 plus Cn a to the nv is equal to 0. Now let's again apply some power of a. Have a guess, what power of a should we apply to this? And don't forget to hit that like button while you're thinking. Like button and subscribe for lots more fun math content. And the hype feature also helps a lot. I'm really loving creating all this free accessible math education, and I want it to reach and help so many people. That's my ultimate vision and goal for the channel. So what we can do is we can act on this equation, we can apply a to the m minus 1. Okay, so apply a to the m minus 1. Then we've just done that already. So that's not going to do anything for us. That's going to make everything 0. Let's apply a to the m minus 2. Okay, so let's apply a to the m minus 2 on both sides. So a to the m minus 2 times c1av plus dot 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 plus cn a to the nv. Okay, that's going to equal to 0 because a to the m minus 2 of 0 is just 0. So what happens now, we're going to get c1 a to the m minus 1v plus dot dot dot, okay, plus c2 a to the m times v plus dot 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 plus cn a to the m plus n times v is equal to 0. And now we're very close because we have the same idea now. A to the mv was 0 and m was minimal with that property. So that means a to the m minus 1v is non-zero. All the other vectors are 0. They're all equal to 0. So therefore c1 has to be 0. Otherwise you can't scale a non-zero vector and get 0. So therefore c1 is equal to 0. Now you can turn this into an induction proof, but I'm not going to rigorously do that. But proceeding in this way, we can keep going. We can show all the coefficients as 0. Ultimately, we just get the relation Cn a to the nv is equal to 0. And that, of course, implies that Cn is 0 because we know a to the nv is non-zero because m was greater than n. And so there you have it. Okay, so that means all the coefficients are 0. And you have n plus 1 vectors in Rn. They're linearly independent. That's impossible. They have to be linearly dependent. So therefore we have a contradiction. Therefore we know that our original hypothesis was false and a to the n was equal to 0. And that's such a beautiful proof. It's just, imagine doing it with matrices. It would just be so messy. How would you even proceed? How would you say for a 5 by 5 matrix, how would you say if a to the 7 is 0, then a to the 5 is 0? How would you do that? Very, very tricky to see how to do that because you have to calculate these matrix powers. But with these principles, it becomes so nice and neat. That's the beauty of math, the beauty of linear algebra. And a huge thank you so much to Stefan, Alex, and Nathan for their ongoing support on Patreon. Stefan for Ruby support, Alex and Nathan for gold support. It makes a world of difference to the channel because I currently do everything on my own. And I just feel so happy whenever I get support like that on Patreon or on YouTube channel membership. Thanks so much to Aman, Shabid, Enehota, and Rob for their ongoing support on YouTube. It makes a world of difference. I'm so grateful for all the support. As a small thank you, there are exclusive perks that come with joining a membership, and any contribution really helps because right now I do everything on my own. I love doing it, but it really helps if I can start outsourcing some work, start hiring editors, start creating mass production with this material. Doing everything on my own in my free time is fun. I really enjoy it, but I really want to try to focus on the math and try to just help me to sort of edit stuff and also to really outsource and outreach. Ultimately I want to make math fun and accessible to all kinds of audiences, reach all different kinds of people and just to go beyond. And any support on Patreon or YouTube really makes a huge difference. So huge thank you so much to everyone supporting and everyone who likes, watches, subscribes. Thank you so much for all your support. It makes so much difference. If you watch this far, I'm so grateful. It really helps support my vision of infinite free accessible math education. I've got 2 fun videos for you now. And the first video you're going to love. It's going to be a proof. It's one of the most beautiful proofs I've seen in math. Maybe the most beautiful. It's a proof that the least common multiple of 1, 2, 3, all the way up to n is greater than 2 power n minus 1. Not only is this statement not obvious, it reflects deep properties of the distribution of prime numbers, and the proof can be understood by anyone with the basic familiarity of integration in calculus. You're going to love this, okay? It's so creative. Check it out. It's going to pop up on the screen here. Here's another fun math proof you're going to love. It's an introduction to the comb space in topology. Okay, it's topology. That sounds fancy. Don't worry. I break it down and make it so easy. The comb space is like an infinite comb, and it actually turns out that it is connected but not path connected. Somehow it's connected, but you can't join 2 points with a path. Check this video out. It's going to pop up on the screen here.